Hi everybody, it's Ajanette and I am here to cover chapter 13, which addresses inferential statistics. So this will be interesting. Let me make sure that this is, yeah, we're good. Okay, so anyway, this will be interesting for some of you. If you've taken behavioral statistics, it'll be a review. If you've taken math statistics, it might seem a little intense, and hopefully we're planting some seeds or watering some seeds. I highly recommend if you took math that you take another behavioral statistics course when you transfer, because you're going to need it. The Math 140 will not adequately prepare you. So it's really important to take statistics from a research methodology perspective. So just my thoughts on that. That being said, let's dive in a little bit. When we talk about statistics, we're really talking about inferential techniques that allow us to make inferences about the population based on sample data. It's impossible for us to collect data from every single person in the population, so we work with samples. And those samples are reasonable approximations of what's happening in the corresponding population. And so we typically have data representing samples. We reference that as statistics, right? The numbers that correspond to samples are statistics. The numbers or data that corresponds to populations is referenced as parameters. And inferential statistics really is the way that we are determining how well those samples match those populations, or how well the samples match one another or differ from one another. So ideally, in a perfect world, studies are conducted and replicated and reinforced through other research that helps to support and affirm the results of our research, right? But what we want to do is we're trying to determine whether or not that sample really reflects what we would expect to see in the population, or is there a difference due to our treatment? Okay, so that's technically what we're doing with inferential techniques. It is important to know that most inferential techniques that you'll be taught at this level are parametric statistics. So they all are making some assumptions or drawing conclusions about the population. You do have non-parametric statistics or techniques that you may have learned, like chi-square analyses, that do not require parametric data and allow us to just use all of the information we know about the sample or our expected alternate or null hypothesis to drive those analyses. So that being said, inferential statistics is based on this assumption of equivalence of groups, right? And we try to manage that through appropriate research protocols and appropriate statistical techniques. The only thing that should differ between the groups is our testing variable, our experimental variable, when we're conducting a true experiment. And how we do that is obviously we adhere to control and manipulation. We try to control all outside factors that might influence the performance and might influence the outcome of the study. And then additionally, so the way in which we collect the sample from the population is called sampling, right? That's our recruitment approach. We want to use random sampling, and then once we have that sample, the way in which we assign the participants to groups is called random assignment. And when you use random assignment, it equally distributes individual differences from those participants between the two groups, right? And so the groups are then therefore equivalent because any individual differences are randomly assigned and evenly distributed or dispersed. And because of that equivalence, then we can determine that differences between the groups then are therefore due to our treatment and not by nature of the participant differences. So remember, there's always some degree of difference, right? A sample is never going to be exactly what equivalent or equal to the corresponding population. It's a reasonable match or estimate, but there's always going to be some difference, and we call that sampling error. It's that natural discrepancy between the population and the sample, and there's a reasonable amount of difference to expect. And so when we're using inferential techniques, we want to know, is the difference beyond that which is reasonable? Is it due to chance, or is it potentially due to our independent variable, right? And so if in fact we know that those groups are equal, then any change in our dependent variable or outcome variable is said to be due to our independent variable. So inferential techniques allow us to calculate or estimate the probability that that difference truly reflects, our treatment effect or just random error. Okay. So when we're working with any kind of inferential technique, we engage in what's called hypothesis testing. We, as researchers, have a research question and we have a stated prediction of what the outcome is going to be, and that's what we call our hypotheses. In statistics, we operate from two separate hypotheses, a null hypothesis and a research hypothesis, or also called an alternate hypothesis. And that's symbolized by H, subset 0 or subscript 0, meaning null, 0, null, nil, zilch, and alternate or research hypothesis meaning 1. Now, from a research method standpoint, we operate under the alternate hypothesis. We are assuming that our treatment has an effect, right? The reason we're doing the research, the reason we're implementing the treatment or going through the program is for the anticipated effect and outcome. Statistically, though, when you talk about, oh, there's going to be an effect, oh, there's going to be an earthquake, well, I don't know if it's going to be a magnitude of 1, 2, 3, 4, 5, 6. I have no clue, right? I can't possibly test every possible outcome, but what I can test is that if you said there wasn't going to be an earthquake and there was, I can test that, right? So inferential techniques are based on an assumption that the null is true, and we're disproving the null. We're saying there were no differences between groups. There was no treatment effect. And mathematically, if in fact my scores fall into those critical regions, they're saying, hold on, it is different. There is something different about this outcome than what would be expected in the corresponding population within a reasonable range. And therefore, it's quite likely that your results are due to a treatment effect, okay? So our null hypothesis is a prediction that there are no differences between groups, means are equal to one another, no relationship between variables. It's nil, nilch, nada, 0, right? All differences are just due to random error, okay? No other reason. The alternate hypothesis is the exact opposite. No, the reason they're different is because of our treatment effect. It's because our IV does in fact cause a change in the DV. It's because the group differences that were predicted are accurate, right? And there is a relationship between variables. So we are always in inferential statistics testing the null. And then because we test the null, then what we do is we reject the null and we say, oh, there are in fact differences. So we are rejecting the null. There is a treatment effect. Or we fail to reject the null. Sometimes it's called retain the alternate hypothesis, but it all centers around the null, right? So when we actually reject the null, we don't say that in research methods. We say that statistically speaking, we reject the null. But in research methods, we say there were statistical significantly, or the groups were statistically significant different, There were significant differences between groups. So we speak in terms in our research methods writing in terms of statistical significance. And so when we reject the null, things are said to be statistically significant. The probability of finding that error was less than whatever our alpha level is, commonly 0.05. If we failed to reject the null, there was no statistical significance. So we failed to reject, no statistical significance, and the probability of finding that score was greater than 0.05. When there is statistical significance, what we're saying is there was such a small degree of probability that the differences between the groups was due to error. In fact, there was the opposite. So if I had a 5% probability of error, 5% alpha level, then I had a 95% probability that the results were due to my treatment effect. If I had a 1% alpha level and probability of error, then I had a 99% probability that my results were due to my treatment effect. We never say 100%. We are dealing with probability theory, so we're always speaking in probabilities. We always, as researchers, allow for the notion of error, right, discrepancy, but we want to minimize that and control that as best as possible with sound research approaches and appropriate statistical techniques. So when we're talking about probability, it's like how likely is something to occur. In statistics, it's really testing the probability of getting that result. What's the probability of getting that result just due to random error? Not the IV, but just due to random error. And we call that our alpha level or our p-value. If the probability of getting that was less than our stated alpha level or p-value, we reject the null. So if we establish a 5% probability, p is less than 0.05, and the probability of getting our score was actually 0.02, then we would reject the null because the probability of getting our number was lower than the alpha level that we established. So alpha level can also be called a criterion sometimes, but it's basically saying how likely is this result, or what's the threshold we have to meet in order to reach statistical significance? How likely does it have to be for us to determine it was significant or for us to reject the null? Most commonly, it's 5%. You do see more contemporary research at 1%, and if the results are below the alpha level, then it's said to be statistically significant. So sample size can definitely affect the strength of the relationship. If you have a really small sample size, like if you only surveyed 2 people, you may not have strong enough information to find significance. And so it's really important that you use an appropriate sample size. Typically, the rule of thumb is about 30, right? Once you have about 30 people in your sample, it's a good approximation of the population. So larger sample size is going to give you more power to find significant results. So stronger relationships and larger samples are more likely to reject the null. And you have a lower probability of getting those scores. So if you don't have a large enough sample, though, you might have really weak results, and so you're not going to be able to detect significance or detect your treatment effect. So, but it's also important to note that if you have a really strong relationship, or a really strong relationship between the IV and the DV, even a small sample is likely going to show a significant result. So there is that kind of relationship between sample size and treatment effect or treatment strength. So let's talk about the difference between statistical significance and practical significance. So I want you to know, in research methods, I really avoid the word significant. You know, when something's important or meaningful, I try not to use the word significant because it has such a specific meaning and connotation in research methods. We talk in terms of statistical significance. When something is statistically significant, that means our results are strong, we have a treatment effect. It doesn't necessarily mean they're strong. It means we have a treatment effect. The probability of getting that score was low. But we often don't know the strength of that treatment effect until we do follow-up tests called effect sizes, right? Effect sizes let us see the magnitude of that treatment effect. So our statistical significance test tells us, was there an effect? And then an effect size tells us how strong that effect was. And so even though something might be statistically significant, practically it might still just be like, oh yeah, big deal, we're in California, so a 2.0 or a 3.0 is no big deal. Whereas someone else coming from a place that's never experienced earthquake, it's like, holy shit, right? And they're scared out of their mind. So it has huge practical significance to them, even though it wouldn't be that big of a deal to us. So I want you to keep those things in mind, that, you know, these two aren't interchangeable per se. When we talk about a sampling distribution, this is a theoretical distribution. It's assuming every possible combination of scores for a given sample size from the original population to produce a distribution of means, where instead of plotting the individual scores on a distribution, we're now plotting the means for individual samples. So each score represents a group of participants and that average within the group. It creates a probability distribution that in fact is a normal distribution based on central limit theorem. And because of that, we can use it to make determinations about the probability of finding any given score, and that this distribution occurs when the null is true. So when something falls into those critical regions, then we can reject the null and it's said to be a statistically significant result. So let's look at a couple of distributions. Here's a population distribution, right? We're going to sample of the entire population, 200 people. This now becomes the distribution of scores based on only the 200 people. Notice the shape of it, although this isn't a curve, right? The shape of it's very similar to the population. It has a sample of over 30 people, so it's a good approximation of the population. Now what we're going to do is we're going to look at the original scores and we're going to do every possible sample. This doesn't give us a sample size, it's saying 100, right? And now notice what was a skewed distribution becomes more of a normal distribution. And so because of that theoretical sampling distribution with an infinite number of samples, because we know that there's certain facts about a normal distribution, such as the mean, median, and mode all equal one another and a line right in the middle such that 50% of the scores fall above and 50% of the scores fall below, that about 70% of the population falls within one standard deviation of the mean, and about 95% of the population falls within 2 standard deviations. So in a two-tailed test where we're looking at both ends, where scores are expected to either go up or down, improve or decline, then less than 5% of the population is going to fall in those extreme areas, what we call critical regions, okay? And so all tests, regardless whether it's a t-test, an f-test, a Pearson correlation, all tests are subjected to the significance test to see, does it fall in the critical region or doesn't it? Let me go back one. When we talk about a two-tailed test, that critical region is divided equally on both ends of the distribution. In a one-tailed test, it's a directional hypothesis, so we're predicting scores are either going to improve or decline. And so we would pile up that critical region on whatever side of the distribution that we're predicting. If it's going up, we'd pile it up over here. If we expect it to go down, we'd pile it up over here. And so that's called a one-tailed test. Okay, you need to know the difference between a one-tailed and a two-tailed test. Directional hypotheses use one-tailed test. Just a hypothesis we expect differences is going to be a two-tailed test. So let's talk about a t-test. A t-test is when you're comparing two groups and you want to see, are those groups different from one another? What we're looking at is the means or averages of each of those groups. And it's great when you have just a control group and an experimental group. It ends up being a ratio. So we look at the group differences, how are they different from one another, divided by the within group variability, how much variation is there within those respective groups, and that's our t-value. So when the null hypothesis is true, then you expect the difference between these two things to be 0, right? If there is no differences, then the group differences would be 0, right? So my t actually is going to get bigger when my group differences are bigger because my numerator is bigger. And my denominator represents random error. So when I control for that and I minimize that and I keep that small, this is a smaller denominator, so my t-value is going to be bigger. This is actually going to be, well, when looking at formulas, it's actually influenced by your standard deviation. There's 3 different types of t-test. A single sample t, where I'm comparing a sample to a population. A dependent sample t, also called a repeated measures or within group, or a paired sample t. Depending upon what book or who taught you, you may have heard it referred to in different ways. This is where I'm doing a repeated measure. That's why I like that name, because I'm taking, it's like a pre-test, post-test. I take a measurement once and then a measurement again, and I'm looking at those mean differences from measurement 1 to measurement 2. Independent samples mean they are completely independent of one another. The people are not the same in either group. Here the people are the same in both measurements, right? I'm measuring Ajanette once and then Ajanette after. I'm measuring Bob before and Bob after. I'm measuring Jose before and Jose after, right? In an independent sample, I'm measuring Bob and Jose and I'm comparing them to Ajanette and Peter, okay? So 2 different means from 2 different samples, and I'm going to look at the differences between those means. So when we write a null hypothesis, we write it in terms of statistical notation and often using parameters or population data, right? So here I'm saying the mean for the sample equals the mean for the population. In the alternate, I'm saying it doesn't. Here, I'm saying the mean difference between the groups is 0. And here, the alternate, I'm saying, no, it's not, right? So the null is always nothing, and the alternate is always not nothing, okay? And in independent samples, I'm saying the mean of the first sample is equal to the mean of the second sample. And in the alternate, I'm saying, no, not nothing, okay? Degrees of freedom are this is defining it as the total number of participants minus the total number of groups. Honestly, that depends. It depends on what type of t-test you're doing. In general, it tells you how many values are free to vary, assuming the mean is known. So once the mean is known, then it's fixed, and you plug it into an equation, and not every number is free to be anything. That mean now locks down at least one of the numbers. And so we have to know degrees of freedom when we're looking at the critical value tables, whether it's the unit normal table or the t-distribution table or the f-distribution table. But we have to know the degrees of freedom. So every test has a different formula for the degrees of freedom. Your book even talks about this as the t-test. Well, actually, that's not true. This is the t-test, independent samples t-test. The dependent samples t-test doesn't have the same formula for degrees of freedom. So your degrees of freedom formula varies from test to test to test, okay? Going back to the one-tailed versus two-tailed, so again, one-tailed corresponds to if you're predicting a specific direction, right? So the values fall on one side, you put your whole critical region on that side rather than dividing it in half and splitting it between the two tails. We use a two-tailed hypothesis if we have no reason, no evidence to support a particular prediction or direction of an outcome. So this is what a sampling distribution looks like with 18 degrees of freedom. This is for t-values. So t-values can be positive or negative. In a two-tailed test, assuming I use a significance level or an alpha level or criterion of 0.05, notice same concepts, just different words. Then I take that 0.05 and I divide it on both ends of the tail. And so 2.5% over here, 2.5% over here. The t-value that I'm looking for is if the value exceeds 2.101, then it's in the critical region, or if it's less than negative 2.101. Same thing here, but only now I'm looking at a one-tailed test, so I'm predicting scores are going to go up. And so I put my entire 5% on that end of the scale. And so now I just have to have a score above 1.734 in order to have a significant result, okay? But again, research has to support using a one-tailed hypothesis or a directional hypothesis, okay? Another test is the analysis of variance, also known as the F-test. F-test is related to the t-test. You can do it when there's only two groups, but we typically see it when there are 3 or more groups. Each IV has to have at least 2 levels, or if there's a factorial design where there's multiple IVs, each IV has at least 2 levels. It, like the t-test, is a ratio. It also is a ratio of variances. So it looks at systemic variance or between groups variance divided by within groups variance or error variance. So we symbolize that by the mean of squares, the mean square of B or the mean square within. The mean square between groups divided by the mean square within groups. Larger F values are more likely to be significant, and F values are positive distributions. So they cannot be a negative number. They are only positive numbers, okay? Just like the t-test, you have different F-tests. You have an independent measures where you have different people in different groups. That's what we call a between subjects design, where you have, Bob and Susie in one group and, Hillary and Jose in another. Repeated measure goes back to that like pre-test, post-test. The same people are measured repeatedly. This is what we call a within subjects design, where the same people are within each of the levels or measurement periods. A factorial ANOVA is when you have multiple IVs. So a one-way is when you only have one IV. A factorial is when you have more than one IV. We also have a one-way and a two-way when you only have 2 IVs. We're going to actually do a two-way ANOVA at some point. And each IV in a factorial design has a significance test, a significance statement. We call that a main effect. So if you have 2 factors or 2 IVs, factor A and factor B, IV A, IV B, factor is just another word for IV. You have a main effect for A, a main effect for B, and an interaction between A and B. So factorial ANOVAs allow you to examine the effects of multiple variables on a dependent variable independently and simultaneously. So nothing occurs in bubbles, right? very rarely is something about a relationship between an IV and a DV. It almost always is about contextualizing and interacting with other variables. So an ANOVA, a factorial ANOVA, allows us to look at multiple relationships in a single test. Now there's follow-up tests that we do. Ultimately, you have a separate F value and a separate P value for every single main effect and every single interaction. And so you can have a main effect for A and nothing for B. You can have a main effect for B and nothing for A. They can both be significant. They can both be not significant and the interaction significant. Any combination of results can occur, but it's all going to determine, it's all going to be dependent upon how large your F value is. Okay, typically, the larger the F value, the more likely we are to reject the null, the more likely it is to be significant. Because you have two or more groups, the F-test tells us that there were differences between the groups, but it doesn't tell us which groups were different from one another. So what we have to do is a post hoc analysis. So we have to see, is group A different than B? Is group A different than C? Is group B different than C? And these post hoc analysis allow us to compare every possible combination of groups. And so we do different post hocs. Commonly, you see, your book, I think, talks about Tukey's, Fisher's, and Bonferroni, but it doesn't talk about Chaffee. I added Chaffee because that's important. That's a really common one. It's a much more rigorous test. It holds them to higher standards. But when we do our reporting in a research paper, we report the significance value for each F-test and for all post hoc tests that apply. If the F-test is significant, we have to do a post hoc analysis to find out which groups are different. Now, looking at a correlational study, correlational studies are not comparing groups. We never break people into groups. We never look at predetermined groups and how people differ from one another if they come in a predetermined group, like a quasi-independent variable. We only look at measured variables. So all our data is quantitative, and we need at least two variables, and we're trying to compare or trying to assess the relationship between those two variables. The most common correlational technique is called a Pearson product moment. It is notated with a small r. When this r represents a sample, the p or rho represents the Greek corresponding, the parameter. So this is a statistic and this is a parameter. The null hypothesis is rho equals 0 and the alternate is it does not nothing, okay? Correlations produce what we call a coefficient. The coefficient tells us the strength of the correlation and the type of the correlation. They range anywhere from -1, imagine a number line, -1, zeros in the middle, to +1. Those are your boundaries for your correlation. -1 tells you that they have a negative correlation. They go in opposite directions. As one variable increases, the other decreases. As absences increase, grades decrease. The other one is a positive correlation, so they go up or down together. They go in the same direction. Study time increases, grades increase. Study time decreases, grades decrease. It doesn't matter if they're going down together. That doesn't mean it's negative. As long as they're going in the same direction, it's always positive. Negative is when they're going in opposite directions, right? Kind of like me and my ex. We were constantly battling, constantly. I said up, he said down. I said black, he said white. We're always going in opposite directions. We had a toxic relationship, okay? So the strength of the correlation is based on the absolute value of the coefficient. So the symbol means nothing. The larger the number, the closer it is to 1, the larger the absolute value, the stronger the correlation. So this is a perfect positive correlation. As one variable is increasing, the other is increasing as well. This is, this is a strong negative correlation. As variables are decreasing, as variables are increasing on X, they're decreasing on Y. And so the numbers are tightly packed for stronger correlations and spread further out for weaker correlations. So this bottom right shows you a 0 correlation. Those variables aren't showing any kind of pattern. Pearson product moment is testing linear relationships. So when you see, hey, I can draw a reasonable line through these, it's likely correlated. So when we talk about correlations, as I mentioned, they describe the strength of the relationship. So a 0 means they have no relationship. The shoe size is not related to IQ. Okay. So once we determine the coefficient, we will do a t-test to determine whether or not that correlation coefficient is significant. Can we reject the null or not reject the null? And so we will use, this actually encourages you to use an alternative program. We here at MSJC or the other colleges where I teach will use SPSS, okay? As I mentioned earlier, effect sizes are essentially looking at the magnitude or strength of the treatment effect. And so whenever you have a significant result, you calculate an effect size. For a t, here is the effect size for a t-value. We can also use Cohen's d, which is a pretty common effect size measure. It tells us the number of standard deviations that the treatment effect caused. How many did it cause it to increase means or decrease means. The bigger the d, the better. The bigger the t, the better. The bigger the f, the better. The bigger the r, the better. Larger scores mean a stronger effect. So size does matter in statistics, okay? Overall, when we're talking about statistical significance, bigger t's are more likely to be significant, bigger f's are more likely to be significant, bigger z's are more likely to be significant. That allows you to determine, do I reject my null? Do I fail to reject my null? How confident am I that my results are due to my treatment effect or due to chance? So that alpha level matters. 0.05 is the bare minimum that you should go. 0.01 is more common nowadays, but it lets us know when we're using an alpha level of 0.05, that's saying we have a 95% chance that our findings are actually due to our treatment, but we also have a 5% chance of making an error. So when we choose an alpha level of 0.01, that means we have a 99% chance that our results are due to our treatment effect, and only a 1% chance of making a mistake or error. So we want to use an appropriate alpha level, but there's trade-offs, right? So when we talk about due to error, when we reject the null and the null wasn't true, that's what we call a type 1 error. Type 1 involves rejecting the null. Type 2 involves failing to reject the null. Type 1 is saying that there was in fact a treatment effect and the drug worked when it didn't. And type 2 is saying that the drug didn't work, the treatment didn't work, but it really did. My sample size may have been too small to find that significance, but it was there. So we can either reject the null or accept the null or fail to reject the null. And we could either be correct or we could be wrong, right? So this is a really good table that lets you know, here I'm rejecting the null. That could be a correct decision. The null truly was false. My treatment did work, so that was correct. But if in fact my null is true and I rejected the null in error, that's called a type 1 error. That's your alpha level. You're controlling that. You have a less than 1% chance or less than 5% chance of making a type 2 error, a type 1 error based on the alpha level. Now, the opposite is true if I accept the null, or I fail to reject the null is how you may have been exposed to it in stats. And that null is in fact true, right? I accepted it and it was true. That is just 1 minus the alpha level. So that is a correct decision. But if I fail to reject it, I accept it, but it really is false, that's a type 2 error. You have to know the difference between type 1 and type 2 error. Type 2, I reject the null in error, I make a mistake. Type 1, I reject the null in error. Type 2, I fail to reject or I accept the null in error, and I shouldn't, okay? Okay, so type 1 errors, just another view at it. From a jury standpoint, type 1 error is when I'm saying guilty, right? But I say, yes, there was enough evidence. Yes, it was significant. Yes, they're guilty, when in fact they were innocent. I just sent a guilty man to jail. Type 2 is when I set a guilty man free. I could not find enough evidence to convict, and so I say not guilty. I don't say innocent, I say not guilty. There was not enough evidence to convict. So type 1 error is often considered the most egregious error. We want to avoid type 1 error at all costs. So how do I determine what significance level? Maybe I just want to reduce the risk of type 1 error, and so I just say the smallest possible type 1, or the smallest possible alpha level or criterion. That becomes a problem then, because that also means that I could be diminishing my power to find significance when there really is a result. And so we have to be careful about that too. There's a balance. The best thing you can do is look at the other research. What alpha level are they using? They're using 0.01 and then you use 0.05. That doesn't make sense, right? So be consistent. Let other research guide you. That being said, we want to really focus on minimizing the risk of type 1 error over type 2 error. There is kind of a general problem in psychological research in that only significant results end up getting published. We don't publish non-significant results. So there's this file drawer in every researcher's office where they didn't find significant results and they didn't submit it for publication because by and large, publishers don't publish non-significant results. Well, maybe there were a bunch of type 1 errors or type 2 errors. Who knows? Maybe we have more type 1 errors and we say there's treatment effects when there isn't published, and the type 2 errors are hidden in the file drawers. Some argue that, people actually manipulate the number and they engage in what's called p-hacking, where they are manipulating that likelihood to find significant results. And so consequently, we have zealous researchers that are just trying to get published, and the results may not be that significant, right? So one thing that we can do is we can do a power analysis, and that allows us to do a calculation about what kind of sample size do I need? What's my probability of rejecting my null, assuming X sample size and assuming X effect size or strength of the relationship. There's some great power calculators online that can help you run a power analysis. Most often power analyses are ran before a study is conducted. And they tell you what sample size to shoot for, basically. How can we avoid type 2 error? How can we make sure that we have a large enough sample where we can detect significant differences that may actually exist? So non-significant results, we don't really say we accept the null. What we end up saying is we fail to reject the null. We don't really say the person's innocent. We say not guilty. And so we really don't, that's our primary focus, is we want to reject the null. But in research writings, we would say there are not significant differences, or there is not a significant relationship, okay? Again, not everybody supports null hypothesis testing, particularly because we can misinterpret that p-value, right? People misinterpret it as the p-value is the probability that the null hypothesis is true, and that's not it. We're really focused on, were the results due to chance or were they due to our IV? So there's not like we say 5% or 1%, but in reality, is there a rigid line? Maybe a 2% when I had a 1% is just as meaningful. And by dismissing it, I'm not analyzing it appropriately or considering it appropriately. Confidence intervals are likened, we use them similar to effect sizes, where it gives us a range of what our predicted population score is based on our sample. So we say, based on X, Y, or Z probability, right, the corresponding population value lies within these boundaries. So I think of it like a field goal post. And when the boundaries are really small, I have a lower confidence level or lower probability of being able to shoot that football. When they're a broader range, a wider range, I am more likely to get the ball in between the posts, right? So it's directly related to your confidence. Probability increases when your boundaries increase. Probability or confidence level decreases when your boundaries shorten. Okay. There are other alternatives than inferential statistics and hypothesis testing. One is Bayesian statistics. I'm not as familiar with Bayesian statistics. I know my son, who's a math major, talks about it a lot. But they actually do probability testing before, and you know, they actually have specific probabilities or estimations of outcomes, which I find to be fascinating and interesting. But I don't love math that much to figure out how to do it. But as a researcher, when the time comes, I'm going to obviously have to learn and make adjustments. The other alternative is replication, right? We do not pay attention to just one single result. We want to make sure it can be replicated. It's reliable over time. And when you have multiple studies getting the same results, then that actually affirms those results being accurate. So we do have a bit of a problem in that we can't replicate every single study. And, you know, science evolves and we have cumulative knowledge over time. And so we want to make sure that we are taking that newer knowledge into consideration. We also need to be mindful of the systemic problems that exist, including racial bias, gender bias, that exists in the literature. Most of what we know in psychology has been based on research conducted on white male college students who do not represent the average American population today. So we do need to be mindful of those things. Couple of computer programs you might be exposed to over time. SPSS is what you'll be exposed to here with me. R is fairly common. SAS, there's also PSPP that's not listed in your book, but that's also used. Some people use Excel to run statistical analyses, and that's fine. Their appearance may differ, but they have that general spreadsheet feel and look to them. So your columns are always like different variables or different pieces of data, and your rows always represent participants. So there's some continuity and consistency. Don't stress out if you go to another university and they teach under a different system. You know, one, you'll have a good opportunity to acclimate into another. It's hard to know what test do I take or do I use. Your design matters. So you have to look at, you know, what scale of measurement is your independent variable, what scale of measurement is your dependent variable, how many groups do you have, or how many levels of the IV are there. When you have multiple IVs, you have to consider that as well. And so these are some great charts to let you know when you're going to use chi-square, t-test, and ANOVA or Pearson product moment, or down here when you have multiple IVs when you're going to use regression or ANOVA. These are the most common that you're going to see. We also have structural equation modeling and other more complex inferential statistics that are used down the road. But we've given you a good start. Hopefully your brain is not throbbing and you're going to do okay. And then I will look forward to talking with you more and seeing you put these into action in our lab and our actual papers. So have fun.